Hello, welcome back to Decaf-Math, ASMR, and a warm welcome if you are new here. I hope that you are doing very well. Today I wanted to show you a cute little application of prime factorization, which we've kind of talked about a bit here on this channel, so I thought that this would be a fun little exercise. And we will take the prime factorization of two numbers and use them to help us find the greatest common divisor, GCD, also known as the greatest common factor, GCF, and also the least common multiple, the LCM of the two numbers. So, as usual, there's no pressure here in the Math Nook. We're just here to have a little bit of fun, and first and foremost, I hope that this brings you peace, 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 comfort, 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 a little bit food for your curious mind, and most of all, a reminder that you are wonderful and very, very loved. So, follow along with what you find interesting. Let the rest just wash around you. And if you need the rest, I encourage you to just close your eyes, and allow yourself to drift off to sleep. So, it does not matter if this is easy for you, if you've never heard of it, no matter here. I will go over what GCD and LCM mean. Let's get started. So, let's start with two numbers, 42 and 48, and then we can do the same method for two larger numbers. So we have greatest common divisor, greatest common factor, two ways to say the same thing, and you might even be familiar with another phrase for it, but a divisor and or a factor is basically a number that goes into the number that we are looking at a whole number of times. So when you think of factors, you should think of your counting numbers, no fraction, no decimals. And basically, if something is a factor of the number we're looking at, it goes into it a whole number of times with no remainder, or in other words, a remainder of 0. Another way of putting that is that if you can come up with two numbers that multiply to be the number you're trying to factor, two whole numbers, again, no fractions, decimals, etc. If you can find a pair of numbers that multiply to be that, they are each considered factors. So for instance, 6 times 7 is 42. So 6 and 7 are factors of 42. Factors often come in pairs. Sometimes if it's a perfect square, like 36, 6 times 6 is 36. 6 is a factor. But the rest of the time, factors come in pairs. So you can keep that in mind. And so if you're trying to check whether or not a number is a factor of the number we are looking at, for instance, 5 is 5 a factor of 48. You can just do 48 divided by 5 and see if there's a remainder, or if it goes in a whole number of times. In this case, 5 goes into 48 9 times, and 9 times 5 is 45, leaving us a remainder of 3. So it's not a whole number of times. So 5 is not a factor of 48. 5 does not go into 48 a whole number of times. So you can list out all the factors of each of these numbers by hand just by going 1, 2, is 3 a factor, is 4 a factor, is 5 a factor, yes or no, 6, 7, 8, 9, 10, all the way up to the number itself. So by this definition, notice that we can never have a factor that is larger than the number we are looking at. Like 49 will never be a factor of 48 because you would need a fraction to cut that down to 48. So at most, you go from 1 is a factor of everything, and the number itself is a factor of anything, and then everything else, all the other factors lie in between. So you can list this out, and the greatest common part is exactly what the name implies. It means that you want to find all the factors that are in common with both numbers, and you want the largest one that is in common, the largest common factor. So you're thinking largest number that goes into both common. So the least common multiple, the LCM, is kind of the other way around. Least common multiple. You are looking for numbers that this goes into and this goes into. So multiples, let's take something smaller like 3. Multiples of 3 are 3, 6, 9, 12, 15, etc. 3, 6, 9, 12. Because 3 goes into 3 once, twice, 3 times, 4 times, Multiples can be 0, 0 is a multiple of everything, and negative, but in this context we only focus on positive multiples. So as long as we have the multiple of the number we are looking at, we're just talking about that number times a whole number, okay? So again, you could list out multiples of 42. You'd start with 42, then add another 42 to that, so 84, and then add another 42 to that. I think that's 126. Then it gets kind of larger, 168, etc., etc. Same with 48, 96, something, I think 144. And then for the least common multiple, again, as the name implies, you want the smallest number that these two both go into. So you're thinking the smallest now. Okay, so the largest number that goes into both, the smallest number that they both go into. So keep that in mind as we use the prime factorization. Excellent. Okay, so now it's time to do the actual prime factorization. If you can do this in your head, you can go ahead and do it. But for the rest of us here, we can just take it step by step. So I know it's hard when the person next to you can just go ahead and do it in their head, and you're just like, maybe, blah. But here I encourage you to just start however you can. Just write down what you know, and we can take it from there. So the prime factorization part is, remember the word factors, numbers that go into what we're looking at a whole number of times, but a prime number is one where you can't factor it any further other than 1 and itself. So our first few prime numbers are 2, 3, 5, 7, 11, 13, etc. And if you look at each of these numbers, you'll notice that we can't break them down any further. 1 is neither prime nor composite, so we start with 2, but you can't break down 2 into any other whole numbers except 1 times 2. 3 is the same way. 4 you can though, because 4 is 2 times 2, so that's not prime. But 5, 7, 11, 13, etc., you can't break it down any further except for 1 and itself. So our goal is to keep breaking down this into factors until you reach one of these, because then you can't break it down any further. So we want to get to the root. So it's kind of like our basic building blocks. That's what's so cool about prime numbers. So what I suggest is to just start with any two numbers that you recognize that multiply to the number that you are trying to factor. I just realized that this might be a little cut off, so I'm going to just go ahead and rewrite it further down. Sorry about that. So, like so. Okay, so we're going to start with two numbers. So for 42, let's say I only recognize that 42 is 6 times 7. That is okay. So then what we do is we take each of them. So we start with 6 and we see if it can be broken down any further. So 6, I notice, is 2 times 3. So I'm going to break that down to 2 times 3. And just to make sure that you don't miss anything, I would go 6 and then I would go to 7 before you look further here. But it's up to you how you want to do it, but I'll check 7. 7 is prime. It can't be broken down any further except for 1 and 7 itself, so I'll just circle it. 7, we'll leave it as that. Then we look at 2 and 3. 2 and 3 are both prime. They cannot be broken down into anything further, so I'll just circle those. So the prime factorization for 42 is 2 times 3 times 7. So we just multiplied them together because factoring implies multiplication. And so we can check 2 times 3 is 6 times 7 is 42. So as long as we get prime factors, 2, 3, and 7 are prime, that is going to be unique for the number that we are working on. Your sort of tree here might look slightly different based on what you recognize. For instance, you might have seen that 2 times 21 is 42 as well, and 2 is prime, and did I say 21 or 41? 21 is 3 times 7, so you would get 2 times 3 times 7. So your tree would look slightly different, but your factorization itself is unique, okay? So let's do the same thing for 48. Let's say I only recognize that 48 is 6 times 8. Why not? So instead of staring too much, just go with what you know. If it's even, just go ahead and divide by 2. And I suggest that only because, especially when the numbers get really large, every time you can pull out a factor, you are scaling it down, and the smaller the numbers get, the easier it is to manage. So if you can divide out a 2, that's still really helpful. So we're going to do 6 and 8. 6 again is 2 times 3. And those are prime. 8 you might see as 2 cubed, but if not, you could see that as 2 times 4. My 2 is good to go, and my 4 is 2 times 2. So we trace the tree down until we reached a bunch of prime factors. And if I were to write this out, I have 1, 2, 3, 4 2's multiplied together. So 2 to the power of 4. This means 2 times 2 times 2 times 2, 4 times my 3. And if I were to check that, I just multiplied back out. 2 to the 4 is 16. 16 times 3 is indeed 48. Very nice. So we have the prime factorization of both 42 and 48. Now, we can use this information to calculate our GCD and the LCM. So what we do is for the greatest common divisor, now that we have these basic building blocks, okay, we are going to look for the factors that are in common. Remember, that's what the greatest common divisor is. So we only care about the factors that are in common. What's the overlap between these two? So if I start with 2, I see that I have a 2 here and a 2 here. So we definitely have at least a 2 in common. How many? Well, if this one only has 1 2 and this one has 4 2s, then the limiting factor is 2, just one of the 2's, right? Once we hit 2 2's, this one no longer has 2 2's, so we take 1. We take the smallest exponent of each factor present that's in common. So 1 compared to 4, we're going to take the 1 with us. We move on to 3, which is in both, and we have 1 in each, so we take the 3 with us. It's like I'm plopping them into my little bag. I don't know why I said that, but I take them with me. And then I check the 7. There's no 7 here. There's a 1 7 here, so I don't take the 7 with me. I'm sorry, 7. So you can think of it as 7 to the 0 because that's 1, and 1 times anything is itself. So 0 compared to 1 is 0. But really, you're just looking for numbers in common. So the smallest exponent of each factor present. So that's it. We have 2 times 3, and we use those building blocks to go back the other way. 2 times 3 is 6. So that is our greatest common divisor factor. So if you were to write out factors of 42 and 48 and you find which ones are in common, you will see that 6 is the largest one indeed. But as sort of a check, you can at the least confirm 6 goes into 42 7 times, 6 goes into 48 8 times. So it is a common factor, and then you just trust the process to know that it is the greatest common one. Intuitively, it makes sense though, because again, prime factors are our building blocks, so you can think of it as taking the largest piece of each building block and then making whatever it is that you built, and that will be the greatest common factor. So that's what's really cool about prime factorization. And so for the least common multiple, remember, it's the other way. It's the smallest thing that both of these go into. So this is the other way around. We look at all of the prime factors present, and we take the largest exponent of each. And so we're not focused on overlap. We are focused on smushing it all together. So we'll start with 2's. And in this case, we will take our 2 to the 4, so the largest exponent of each one. And that is because if our least common multiple has 2 to the power of 4 as a factor, then it's definitely also going to be divisible by 2, because 2 goes into 2 to the 4, 2 to the 3 times. So you want the largest one to encapsulate the 2. Then we have 1 3 in both, so the highest power of 3 is 3. And this time we get to take along our 7 because we have a 7 here, and this number doesn't have it, but we want our least common multiple to be divisible by the 7, so we need to include a times 7 here. And now we just multiply this out. We have 2 to the 4 is 16 times 3 is 48. I'm going to use my handy calculator to help me multiply that by 7, so 48 times 7 is 336. So 336 is our least common multiple. Again, we trust the process because we're working with the prime building blocks, but just to check something, we can make sure that 336 is at least a common multiple, if not the least, but it is, of 42 and 48. So to do that, we do 336 divided by 42, and that is 8 times. So it's a whole number of times, no decimals or anything. And 336 divided by 48 is 7. So that's a whole number of times, no remainders, no decimals. So we are all good. So that means 6 is the largest number that goes into both 42 and 48, and 336 is the smallest number that 42 and 48 go into. So as you can imagine, if you were to list this out every single time, especially multiples, the numbers would get really large, and then you would have to do cross-checking to see what's in both, what's common, so that might take a really long time. So you could imagine if we did larger numbers to start with, that this would take even longer. So that's why this little trick can be very helpful. Now, I'm going to move on and do a little example with 2 larger numbers. And we will do 588 and 693. I wasn't kidding when I said that these numbers would get bigger. And we'll just work through this a little bit quicker, no pressure, no stress. I'll do all of the work. But now that we've seen how this works, I figured I would just carry this out. So again, if you don't know where to start, just divide by a factor that you know. So this is even, 588 is even, so I would pull out a 2. But I also recognize that the last 2 digits, 88, are a multiple of 4, which means the whole number is a multiple of 4. So I'm going to actually pull out a 4. I like these cute little number tricks, and maybe I'll make a video on it, but 588 divided by 4 is 147. 4 breaks down to 2 times 2 again. And then I see 147, and I notice I have a 14 and a 7. Both are multiples of 7, so this whole thing is divisible by 7. And that leaves me with a 2 and a 1, which breaks down to 3 times 7. So if I combine all of these are all prime now, so I'd have 2 squared times 3 times 7 squared. And that's my prime factorization. 2, 3, and 7 are prime. And to check again, we just multiply it out since it's unique. So 4 times 3 is 12 times 7 squared is 49. So 12 times 49 is 588. So that's good. That's our prime factorization. For the other one, I see I could just pull out a 3 since each digit is divisible by 3. So without doing a lot of work, I just see 2, 3, and 1. Now, to just kind of figure out a factor of this, I see that 2 plus 3 plus 1 is 6, which is a multiple of 3. So the whole number is divisible by 3. Another one of those little number tricks. That's pretty fun. So I'll divide by 3 again. And then I'll just do 2, 3, 1 divided by 3. 77. And that breaks down to 7 times 11, and then these two can't be broken down any further. So combining again, we have 3 squared, 2 3s times 7 times 11. Excellent. So So if you don't already have this habit, I suggest that for prime factorization, you list them by smallest to largest. I don't know if I already said that, but smallest to largest factor, and then raise to whatever exponents you need. And that way it can really help in looking at what's in common, because then you don't have like this one with a 2 over here and then like a 7, and then this one has a 7 here and a 2 here. You have to go searching. The more you can just line it up, the easier it is for you. So the greatest common divisor, greatest common factor, again, we look at what's in common. So we start with 2. There's no 2 here, so nothing. We don't get to take the 2's with us for this. We look at 3's, 3 to the 1 compared to 3 to the 2. So we take the smaller one, this smaller exponent, so we'll carry along a 3. We have a 7 squared and a 7 here, so we take one of the 7's, that's our limiting factor. And then there's 11 here, but no 11 here, so we are done. And 3 times 7 is 21. Hope you can see that. But 21 is our greatest common divisor of 588 and 693. Now imagine if you're trying to list out every single factor here, that would take quite a while. Then you'd have to cross-check and see which ones are in common. Then you have to see which one's the largest, and then you're not really sure if maybe you missed one. And so this is an awesome little trick. And so then for least common multiple, again, this is the largest power of each now. So instead of what's in common, we just take everything we can. So for 2, there's no 2 here, but we have a 2 squared, so we get to take our 2 squared now. It gets to have some fun with us here. And then for 3, we have a 3 and a 3 squared, so we take the 3 squared, the larger one. And then the 7 compared to 7 squared, we take the 7 squared. And then nothing, but then there's 11, so we'll take it along with us. For the least common multiple. So now every factor gets to have a turn, which is nice. And now we just multiply this out. 2 squared times 3 squared times 7 squared times 11. So 4 times 9 is 36. So 36 times 49 times 11. 19,404. 19,404. So now imagine if you're trying to list out a bunch of multiples of 588, 693. That would take forever to get to 19,404, let alone trying to match the lists to see what's in common. So, point being that I still think that this is super cool. Don't know why I keep justifying it, but we can check that that is indeed a multiple of each. So 19,404 divided by 588 is 33. So you would have to write 33 multiples in a list before you even got to 19,404 in the first place. And then 19,404 divided by 693 is 28. So you'd have to write 28 multiples of 693 to even get to 19,404. And by then you'd probably be asleep anyway or already hating math. So that is our least common multiple. That is our greatest common divisor. I hope that this was interesting and cute and relaxing. And I will see you around for more math very soon. And if you are asleep right now, sweet, sweet, sweet dreams. And if you are continuing on with the rest of your day, I hope that you have a wonderful, blessed rest of your day. And I will see you around for more math very, very soon. Bye-bye.